So, welcome back, and this is wave motion lecture number three. Lecture number three, and we are going to start with the next topic, which is quite similar to what we have done in the previous topic. The previous topic was transverse wave. Now, from transverse wave, we have moved on to longitudinal waves. And the best example of the longitudinal wave, just seen in it in questions, is a sound wave. Now remember, in transverse wave, what was happening was wave was traveling like this and the particles were moving perpendicular. Do we remember this? Yes or no? In longitudinal, what is going to happen is sound waves are traveling like this in this direction along x-axis. The particles will also move along x-axis. In transverse wave, we have crest and trough. In longitudinal wave, we will have compressions and rarefactions. Do we remember this? Yes or no? No, yes. I hope we remember this. We have already done this. Now we'll just go through a brief introduction of longitudinal wave. Basically, we'll be dealing with sound waves, and again, I am showing you a part of your sheet only. Longitudinal waves, sound waves. Material medium is required. That is one thing. Sound waves are always longitudinal in nature. What is the speed of sound? 332. Sometimes we take it 330. Sometimes we may take it even 300 to simplify our calculation. Sound is audible only between 20 Hz to 20 kilohertz. That's our hearing range. Sound wave cannot be polarized. Any longitudinal wave cannot be polarized. Do we understand this? Yes or no? No or yes? I'll give you a minute to note these points down. Okay then, just a quick revision of what is a longitudinal wave. Individual particles of the medium execute simple harmonic motion about their mean position in the same direction in which the wave is moving. Sound waves, an example of longitudinal waves, vibration of air column in organ pipe or vibration of air column above the surface of water in resonance apparatus. All these are good examples of longitudinal waves. Do we know this? Yes or no? No or yes? These longitudinal waves, they propagate by the phenomena of compression and rarefaction. Do we know this? Yes or no? No or yes? We have already discussed this. Now is the time to see how does a compression and a rarefaction look like. Well, at some points, the particles are going to be compressed. They will be closer than the nearby particles. The density and pressure, remember, density rho and pressure P are very high. There is a decrease in volume, consequent increase in the density of the medium, and you have an increase in pressure. This region is known as the region of compression. The opposite of compression is rarefaction, in which you will have particles getting further apart, increase in volume, decrease in density, and decrease in pressure. Do we understand this? Between any two consecutive compression or rarefaction, the part difference is known as your wavelength lambda of the wave. Do we remember this? Do we understand this? I'll give you a minute for you to note it down and see it. Let us go ahead and see the equation of sound wave. Well, we can write the equation of progressive sound wave in terms of the change in pressure, or we can also write it as displacement. It is normally not written as the displacement equation. It is normally written as the change in your pressure, because that is what that makes a wave to move forward, the phenomena of compression and rarefaction. So here we have change in pressure delta P will be delta P naught into sine omega T minus x by v, where omega is your angular frequency, T is the time, v is the wave speed, x is the position of the particle, delta P naught is the maximum increase in pressure. There we had amplitude, here we have maximum increase in pressure. Instead of adding delta, if you don't feel comfortable, you can write the pressure at any point. Remember, this is not the pressure at any point, this is the change in pressure at any point. You just add it from the original with the original pressure, you will get the total pressure. Delta P or P will be equal to P naught, where P naught is the amplitude into sine of omega t minus kx. Remember, this is the pressure equation. This is the pressure equation of a sound wave. Do we understand this? Yes or no? I'll give you a minute to note it down. Note it down fast. Well then, the next thing that we got to study is the velocity of sound. Medium is required for sound propagation. Longitudinal wave. The velocity of sound or any wave which is mechanical will depend on the property of the medium. It depends on the elasticity of the medium and it depends on the inertia of the medium. Newton's formula that Newton gave for velocity of sound was v is equal to E by d ka root, where E is the elasticity coefficient of elasticity, and d is the density of medium. But this formula was later corrected. Right now, you just write what is Newton's formula for velocity of sound. It is very simple, root over modulus of elasticity or coefficient of elasticity divided by the density. Do we understand this? Just note it down. Newton's formula for velocity of sound. Well, using Newton's formula, we can easily calculate the velocity of sound in solid or velocity of sound in liquids. For velocity of sound in solids as given in your sheet, page number 208, what you do is you replace the modulus velocity by Young's modulus. Do we remember Young's modulus? And in case of liquids, you replace the modulus of velocity by the bulk modulus. That becomes the velocity of sound in solid, y by d ka root. The velocity of sound in liquid becomes root over b by d. Give you a minute to note it down. Let us move further ahead and see what happens with the velocity of sound in gas. And here is what there was a small problem. Newton thought that to find the velocity of sound in a gas, we'll have to replace this modulus by the pressure P, and he assumed that the temperature of the medium would remain constant. So sound wave motion, he thought that it's an isothermal process. Remember the word isothermal process. So the formula he gave was root over RT by M. But when we found it, when we use this formula for finding out the velocity of sound in air or any other medium, we found that this formula was not correct. So Newton's formula was not applicable. The formula was correct, but the result was not coming same, and hence Newton's formula, where he understood or thought that the sound wave in isothermal process was wrong. His formula was root over RT by M. That formula was wrong. Do we understand this? I'll give you a minute to note it down. Let us move and see what happened. If it is not isothermal, then Laplace came and he suggested that this is not an isothermal process, but this is an adiabatic process. For adiabatic process, the modulus of elasticity becomes gamma times P, where gamma is your adiabatic constant. Cp by Cv. Do we remember Cp by Cv? Yes or no? So he suggested correction that it should be gamma times P by D or gamma times RT by M. With this formula, the velocity of sound became exactly correct, and that is known as the Laplace correction. Gamma RT by M ka root, that is the formula of velocity of sound in gas. I'll give you a minute to note it down. I hope you have noted it down, beta. Well, let us see what are the effects of various factors on the speed of sound, and the most important thing is effect of pressure at constant temperature. Remember, if I increase or change the pressure of the body, I can also change its density. The formula for sound wave, if you look at the formula for sound wave, it is also written as gamma p by rho. From here, you will see or try to understand that it is directly proportional to root over p. But it may happen that you can change the pressure without changing the absolute temperature. Therefore, if you change the pressure but the temperature remains constant, the speed of sound will remain unaffected. Speed of sound, remember, is directly proportional to the absolute temperature. It is not directly proportional to the pressure. If the temperature does not change and the pressure changes, the speed of sound does not change. Do we understand this? Yes or no? Similarly, it is directly proportional to the root of temperature. If you change temperature, it will definitely change. Do we understand this? Yes or no? Number 3, if you have different gases, velocity of sound is inversely proportional to the molecular mass of the gas. This is the third formula you must remember. Do we understand this? The first thing that you must remember, it does not depend on pressure. The temperature is constant. Second thing that you must remember, it is directly proportional to root over T. Remember, this T has to be in Kelvin. Do we understand this? And it is inversely proportional to the root of molecular mass of the gas kept in kg. I will give you a minute to note it down. Have you noted it down, beta? Then the next two, effects are effect of humidity and the effect of amplitude and frequency. On increasing humidity, the velocity of sound increases because density decreases. Velocity of sound in dry air is always less than in humid air. Remember, as humidity increases, velocity of sound increases. Amplitude and frequency have no effect on the velocity of sound. Do we understand this? Can I have some reason that we understand this, sir? I'll give you a minute to note this down, beta. Well, the last thing here that you must see here is the effect of the velocity or the observer or the velocity of the medium. If the medium itself is moving, if there is wind, the medium itself is moving, then the velocity of the sound will change. If the medium is moving in the same direction as sound, the effective velocity will be more. If the medium is moving in the opposite direction as the velocity of sound, the velocity will decrease. Do we understand this? So these are the effects that we have seen. Number 1, effect of pressure. There is no effect of pressure. Number 2, the effect of temperature. Velocity is directly proportional to root over T. Number 3, it depends on the molecular mass of the gas. It is inversely proportional to root of molecular mass. Number 4, density. As humidity increases, velocity increases. There is no effect of amplitude and frequency. But if there is velocity of the medium, then the velocity of sound will get affected. If the medium is moving in the same direction, velocity increases. If the medium is moving in the opposite direction, velocity decreases. Do we understand this? Do you have any doubts on this? Yes or no? No, yes. Well, with this, we come to an end of this particular lecture. on sound waves or longitudinal waves. What we have covered in this lecture is what is sound wave. It's a longitudinal wave. It requires medium. Particles are moving in the same direction. We have seen the equation of sound wave. That equation is returned in terms of change in temperature. Then we have seen what are the effects. What is the speed of sound? Speed of sound is given by Newton's formula in a medium root over modulus of elasticity divided by density. For solid, it is root over y by d. For liquid, it is root over bulk modulus by d. For gases, he said that it will be root over p by rho or root over rt by m. That was wrong. Laplace corrected it, root over gamma rt by m. Do we understand this? With this, we will end today's class. In the next class, we will be moving ahead with longitudinal wave and try to cover as much as possible. I hope you love this class. I'll see you in the next class. Take care and have a nice day, beta. Bye bye.